Welcome to NetworkBadger. Today we will talk about ping and traceroute. A solid understanding of ping and traceroute will be very helpful if you are getting ready for your certification exam, such as Cisco CCNA, Juniper JNCIA, CompTIA, Network Plus or A Plus, or something similar. Or you may be working in the IT industry where ping and traceroute are necessary when troubleshooting a network or doing some research or investigation, or you simply may be a curious one looking to know how things work. Um, so let's start with determining where ping and traceroute reside in the grand scheme of things. If you're familiar with the 7-layer OSI model, you will not find ping or traceroute in one of the layers because these tools are hidden under the umbrella of a protocol called ICMP. ICMP stands for Internet Control Message Protocol. Officially, ICMP belongs to OSI layer 3 right here. However, there is some debate going on about the validity of this classification because OSI layer 3 is responsible for determining a route or a path through the network in order to get something from source to destination, and layer 3 is also responsible for associated addressing, usually IP addressing. But ICMP performs none of those functions, right? It does not determine any route. It has no addressing mechanism, and it actually relies on a layer 3 protocol to work. It will not work without the IP protocol. So, well, you'll say maybe it belongs, maybe ICMP belongs to layer 4 then. Layer 4 ensures that data is transported from source to destination. Layer 4 uses the concept of ports. Layer 4 ports, right, like TCP port 80, port 443, UDP, port 23, and so on. But again, ICMP has nothing to do with ports or data delivery. So it doesn't belong to layer 4 either. If they ask you, remember the official answer is ICMP resides on OSI layer 3. If they ask you, is ICMP a layer 4 protocol? Of course not. Is it a TCP or a UDP protocol? No. Does ICMP use any layer 4 ports? No. The answer is no. So just keep that in mind if asked on an exam, if they try to trick you into an incorrect answer. The reason why classifying ICMP is so tricky is that ICMP was not designed to carry user data. Many protocols are responsible for conveying user data, like web, email, voice, video, files, etc. But ICMP does not carry any user data. It's an auxiliary protocol. It's a tool used by users and systems for signaling, reporting the state of the network, and so on. When I say users, I mean both human users and machines, like computers, servers, routers, and so on. So when looking at ICMP specifications, you will not find any mention of ping or traceroute. Ping and traceroute are unofficial terms for tools that are built with ICMP messages. ICMP has 256 message types, most of which are unused, reserved, or depreciated. For now, we're only interested in 4 message types: echo reply, destination unreachable, echo request, and time exceeded. they have their own unique message type numbers, type 0, 3, 8, and 11. With these 4 message types, we can build successful pings and trace routes. These are like little building blocks for our pings and trace routes. When you type ping on your computer and press enter, your computer will send out an ICMP echo message type 8. That's it. That's how your ping goes out. Of course, your echo request will be encapsulated in a standard IP packet containing the source and destination IP addresses. And there will be 3 possible replies that you may receive in response to your echo request message. Or the 4th possible outcome is no reply at all, right? So you may either receive no reply, or you will get one of 3 possible reply messages. No reply at all means that your request never reached the destination, or the response from your target never made it back to you. No response can also mean that ICMP is disabled on the device that you're trying to ping. That's pretty common for security reasons. Computers may have some draconian firewall enabled that blocks all ICMP, including pings. I recall Windows firewalls were like that. Now they got a little smarter and they don't block ping by default, but I remember they used to do that. If you wanted to ping a computer, you had to disable the Windows firewall on that computer. It is a common practice to disable, rate limit, or deprioritize ICMP on critical network devices like switches, routers, firewalls. You may want your device hidden from hackers or bad guys or script kiddies. If you're not familiar with the term script kiddies, these are like amateur hackers, not real hackers, who just got their hands on bad, stupid tools and use them to harm other people without a real purpose or without real knowledge or understanding of what they're doing. So you may want to hide from those guys by blocking ICMP, disabling ICMP on your device. Or sometimes you will notice a device will respond to a few of your pings and then will stop responding. That way, administrators are trying to conserve CPU resources and avoid spending CPU capacity on unnecessary tasks. So remember, unsuccessful or slow pings may simply mean the ping target does not want to bother responding to you, which doesn't prove there's a network problem. But by default, most routers and computers will respond to pings, and firewalls by default will not respond to pings, right? And I don't mean like application firewalls, Windows firewalls. I mean like hardware firewalls. Those will not respond to pings by default. Of course, you can explicitly allow ICMP, and then they will respond. So that was no reply. The next possible outcome to your ICMP echo request is actually echo reply. That's what you're hoping to get. ICMP message type 0. You're hoping to receive that in response to your echo request. Receiving an echo reply means a successful ping. You may receive a destination unreachable response, ICMP message type 3. That will not come from your ping target. Important to understand, right? That type of message will come from a device which was responsible for forwarding your ping to the destination, but that device determined that it will not be able to complete the task. there's no route to the destination or something like that, so that router doesn't know how to get uh, your ping to the destination, and it will just try to be nice to you and informative, and it'll generate a brand new message for you saying, sorry, but I will not be able to deliver your ping to the desired destination. Don't expect a response to your ping. Um, this behavior is usually enabled by default on most routers, and again disabled on firewalls. So the difference between an echo reply and destination unreachable is that the echo reply will come from your ping target, and destination unreachable message will not come from your ping target. It will come from something else that was responsible for delivering your initial echo request message. Uh, the next possible message is time exceeded, ICMP message type 11. Uh, it will also come from a router somewhere between the source and the destination of your ping. It will never come from the destination of your ping. Let's step back for a minute and recall that any IP packet, and remember ICMP is inside an IP packet, so any IP packet has an expiration date, so to say. When a packet is launched, it has a TTL, time to live, value set. Time to live is a counter that decrements by 1 every time the packet goes one more hop, or every time a packet goes through a router, the time to live timer is decreased by 1. Usually the time to live value is set to like 30 or 50 or more. It doesn't really matter. What does matter is that without the TTL limit, the internet would break. The internet would become filled with lost, homeless, ghost packets wandering around forever. They wouldn't disappear on their own. Uh, they would simply go from router to router to router indefinitely until the internet capacity becomes exhausted. So the TTL value ensures that if your packet doesn't make it to the destination within a preset number of router hops, it must be discarded. And when it is discarded by a router uh, who does the honors of stripping the time to live value from 1 to 0, that router will generate the ICMP message time exceeded. Right? The router that happens to be the last one to touch your packet before the time to live expires will generate time exceeded message for you. So if we ping something and receive a TTL exceeded or time exceeded response, what does that mean in real life? Normally, pings have their default TTL value set to some number between 30 to 100. It depends on the operating system, and you can easily change that value. So in real life, it's pretty much unrealistic to run out of hops and not reach your destination. In the internet, you can get pretty much anywhere, even across the globe, within a dozen of hops or less. If it takes you 20, 25 hops to get to your destination, you should be asking why. That's a lot. So if your ping runs out of hops, that usually means one thing: routing loop. There is a router or a pair of routers misconfigured somewhere, or there's a broken dynamic routing protocol somewhere, causing your ping packet to go ping pong style between two routers, right, back and forth, or in a circle between 3 routers or more. That will guarantee you will quickly run out of your TTL hops and will never get to your destination. Right, so if you're receiving a time exceeded message, rest assured there's a routing loop somewhere on the way between the source and the destination of your ping. So now we know how a ping is constructed. an ICMP echo request followed by a reply message or no reply at all. Simple as that. Now, traceroute. An ICMP traceroute also starts with an echo request, like a ping. But there is something unusual about the echo request used to trace a route. The initial echo will go out with a starting TTL value of 1. Yes, intentionally. We want the first router that we encounter to discard our packet. When discarding, the router will return an ICMP error message, time exceeded. And we will want only one thing from that message, the IP address of the router that sent the error message. We will write down the IP address of the router that discarded our initial echo request, and we'll repeat the process, now setting our TTL value to 2. We expect the second router to drop our message as well and reveal its IP address, and so on. We will keep incrementing TTL by 1 until we reach the final destination. Eventually, we will receive the echo reply message, and that will conclude our traceroute. Right, so a traceroute is just a series of pings with time to live value incrementing by 1. So let's see on a quick animation how ping works. Pretty straightforward. Our PC on the left will generate an echo request. That will reach the PC on the right. And if everything goes well, the PC will generate a reply, we'll receive it. That concludes our ping. This is a very small network, probably a LAN, local area network, but it doesn't matter. These computers may be in the same room, or they may be half the world apart. Doesn't matter, this process will work the same. There may be routers in between, right? So let's insert a router. Complicate our topology a little bit. So we're inserting a router between our computers, and let's imagine our ping is a little broken this time. So again, we start with an echo request. It goes from the computer to the router. This router is directly connected to the PC on the right, but there's something broken. So this router knows that in order to reach the PC on the right, it would have to send out the packet out of the interface on the right, but that interface happens to be down. So the router knows that the only way to get to the computer is unusable. The router knows that for sure because the computer is directly connected to the router. So the router will behave nicely, will try to be helpful, and the router will originate and generate an error message for us. Destination unreachable message, ICMP error message. So we will learn from that message that, well, we cannot ping the device. The device is unreachable. By the way, nobody asked this router for any input, right? The computer on the left was asking a question, was asking something to the computer on the right. Nobody asked the router anything, but the router figured it's a nice thing to do to get involved and tell us that we won't be able to reach the computer on the right. So that is our ICMP message, destination unreachable. Adding another router into our topology here. This time we will imagine that these two routers are misconfigured. Actually, the router on the right is misconfigured. The second router is misconfigured. So we're sending our echo request. Our ping reaches the first router successfully, reaches the second router successfully. Now the second router should be forwarding that ping packet to the destination, to the computer on the right, but there's something misconfigured, so the router, instead of sending the packet to the destination, sends it back to the first router. So this is our routing loop here, and this way we will run out of hops, TTL value will go to 0, and we will receive the time exceeded error message. So our ping will never reach the destination, and it's the fault of the router. So there's nothing wrong with our destination, but there's no path to it. And now let's look at a quick and simple traceroute animation. Simple topology, we have two computers, computer 1 and computer 5, right? Bottom left and bottom right. We will be sending a traceroute from computer number 1 to computer number 5. And our traceroute will start as a regular echo request. And our initial time to live is set to 1. Right, so we want to focus on this time to live value here, and now we will focus on the reply. The first router will respond saying time to live exceeded. The first router knows how to reach the ultimate destination 5.5.5.5, but he's not allowed to proceed because the time to live was so low. The first router that received the packet had to discard it. So the first router responds back to us saying, sorry, time exceeded. Just like on the previous slide, time exceeded. But we expect that. And we expect the time exceeded message from the first router. In fact, all we care about, we want to see his IP address. That's all we need. We intentionally set our TTL to 1 because we want to capture the IP address of the device that will send us the expected error message. Moving on. Now we set our TTL to 2, our second attempt. We increase our TTL by 1. Now it's 2. And again, we know we will receive an error message from the second router. All we want is the IP address of the second router. And here it is. The error message comes back, time exceeded. So this router doesn't know that we're doing a trace route. This router doesn't care whether we're doing a ping or a trace route or it's a regular IP packet. All this router knows that it received an IP packet with time to live expired. So it responds, we capture his IP address, repeat. Now we increment our TTL to 3, same thing. We're getting the error message from the third router 4.4.4.4. And next time, when we set our TTL to 4, we actually reach our computer, and our computer will respond with an echo reply, and we know it comes from 5.5.5.5. That's what we were initially trying to ping or trace route to. So the whole picture will look like this in 1, 2, 3, and 4 steps. So 4 hops here. We increased our TTL from 1 to 2 to 3 to 4. We have accumulated this little list of IP addresses on the left side. This list of IP addresses is our trace route. So we can say tracing from 1.1.1.1 to 5.5.5 took us 4 hops. The first hop was 2.2.2.2. The second hop was 3.3.3.3, 4.4.4, and 5.5.5. This is our trace route. So we built our trace by manipulating the 2 message types, echo request and time exceeded. So that's how ping and trace route work in principle. And now let's look at some real pings and trace routes.